Yes, class. Hello. Is this audible? Khalid, Salman, Samaira,
Yes,
Sneha.
ma'am, here. Yeah.
Alright. So in the last class, we had covered magnetic fields due to different particular shapes. So Salman, do you remember magnetic field at the center of a circle?
No, ma'am, I wasn't really feeling well, so I don't remember much.
Okay. Yes, Salman. So are you fine now?
Yeah, now I'm doing okay.
Okay. And Khalid, do you remember? Anyone? Magnetic field at the center of a circle.
Yes, it's B is equal to U naught I by 2R.
2r, and if it's a semicircle, that becomes 4r in the denominator. Fine. Samira, you were there in the last class, no? So do you remember the magnetic field due to a semicircular arc?
It was U naught I alpha by 2 pi r.
Yes, mu naught I alpha by 4 pi r. All right, 4 is there in the denominator. And for all the cases, if you had n number of turns are there, so directly multiply it with it. Direction also we have studied two methods basically we had seen. One where you put your thumb in the direction of current and curvature gives you direction of magnetic field using your right hand. Other one is you place your fingers along the direction of current and point towards the point whatever you are calculating, and the thumb gives you the direction of current. A thumb gives you direction of magnetic field. So these were the two methods that we had seen. These were the cases that we had seen. Apart from this, we had seen infinite wires, infinite and semi-infinite wires. So Sneha, can you tell us what was the magnetic field due to infinitely charged wire? Yes, Sneha, just try. I'll help you with it. You're not audible, Sneha. See, let's just quickly see. This was the case for infinitely long wire. Difference between infinite, semi-infinite arises by the denominator. In case of infinitely long wire, you have mu naught I by 2 pi a. In case of semi-infinite, that becomes mu naught I by 4 pi a. Then we have a complete circle. For the complete circle, we had seen that it was mu naught I by 4r. For a semicircle, we had seen it was mu naught I by 2r. 2r for it and 4r for it, the semicircle. And then magnetic field at the center of a circular arc, it was mu naught I alpha divided by 4 pi. These were the cases we have seen. And one more thing we had discussed, that if on the axis you take a point and then there you are calculating the magnetic field. So magnetic field on the axis of a straight line wire, whether it is infinitely charged, whether it is semi-infinitely charged, or it is finitely charged. At the axis, since the angle is 0 degrees, sine 0 becomes 0 in your Biot-Savart's law. So your complete magnetic field becomes 0. So if it's on the axis, like this is a line you have, infinitely long wire, at any point anywhere in this, either this or any side of it, if we have it, then consider the magnetic field directly as 0. After doing the circular parts, we haven't discussed any questions, so just let's do some questions first. So you have a straight wire, then you have a semicircular arc, semicircle basically, and then this is the wire is in the shape of this. I current is flowing like this. If required, you can use and take the radius of the semicircle as small r. You have to find the magnetic field. Calculate magnetic field at O point. At O point, you have to find out the magnetic field. So for calculation of magnetic field, consider these as three parts. If you will look at these, no, this as a single part, this as another part, and this as a third part. 1, 2, 3. Then you will be able to notice that all these three figures you are familiar with and you have already done it. So then calculate B1, B2, B3 and then take the sum of it. So just try this out. This is very easy. Since 1 and 3 will ease your calculation. Just try and send your answers. At least B1, B2, B3 separately you all can write down. Hania, do you have the notes for the previous class? I think you were absent, no, in the last two classes, Hania?
Yes, ma'am.
All right. So what was the last class which you attended?
On Monday, last Monday.
Okay, so one class was missed, Wednesday's class.
Yes, ma'am.
All right. So B1, can anyone tell what is magnetic field due to this first segment? Only this. Anyone from the class? Anyone? And you have to calculate the magnetic field at this point O. So consider point O and C. Samira, can you try B1? Nobody. See, look at point O. Point O is lying on the axis of it. This is the axis. This is the axis of this first part. This first wire that you are able to see. So O point is lying on the axis. What did I tell you? Even I revised it just now. Whenever your point is lying on the axis, then your magnetic field because of that part becomes zero. So magnetic field due to this conductor, this segment of the wire, this will be zero. Reason because it is lying on the axis, sine theta is zero. Sine zero will become, in your Biot-Savart's law formula, that will simply be zero. That's why at the axis we take 0 magnetic field. I think I made you write also this. Then B3 will be the same. B3 will also be 0 because this point is again lying on the axis. B2 we can calculate. B2 will be having a value. Now magnitude of a circle, for a semicircle we had discussed. For calculation of magnetic field due to a semicircle, we have discussed it right now also. It is mu naught I divided by 4 times the radius. And radius is already given, capital R. Now quickly write in the chat box what should be the direction because of this. Magnetic field is 0 in this part and in this part, so there won't be any direction. At least tell it for this part. What will be the direction of magnetic field? All of you, quickly in the chat box right now. What should be the direction? Samaira, you are right. Let's check again, check once again. This is the direction of flow of current in this way. Yes, now it's correct, Khalid. Sneha, right? Okay. See, for all those who were not present in the class or who want this part to be repeated, whenever there's a curve, then move your fingers along the curvature of the sense of current, whether it's a circle, whether it's a semicircle, or it's a circular arc. So in the semicircle, if you see, just see it parallel, both of it, the figure and the screen right now. The current is flowing in this way. This is the direction of flow of current, like this. So I have to curl my fingers along the sense of current, and I have to use my right hand. Don't use your left hand, otherwise the answer will be opposite. So if I use my right hand, this is my right hand. This is the sense of current that is flowing this direction. It is flowing in which manner? Even if you can see it is moving clockwise. For all of us, it is moving clockwise. So curl your fingers clockwise. Thumb gives you direction of current. See, thumb is pointing inwards into the screen for me. For me, I am doing it in front of the screen. So curling the fingers, lead the thumb inwards. So inwards is what? Inwards is the unit vector, that is minus k cap. Or you can write inwards as well. So net magnetic field will be what? Net magnetic field will be this only, B1 plus B2 plus B3. Since rest of them are 0, it will be mu naught I by 4R minus K cap Tesla. This much. All right, note it down. Let's do more questions on this, because questions from magnetic field and combination of various other magnetic fields comes a lot in your exam, and not only in your board exam, in your entrances also. Lots of questions you can find out in your previous year's papers of CBSE, as well as other board exams, as well as in your entrances. These combination questions are given a lot. So we'll discuss it. Just note it down first. And whenever you see combinations which you have not seen, like a wire in this form you have never studied, this wire, in this case, you have never studied. So break it into parts which you are able to identify, like the first part, then this semicircular part, then this third part, like this. For all those who do not remember, magnetic field at the center of a circle. This is mu naught I divided by 2. Using this, now calculate the net magnetic field and see the directions of current. So see whether both the magnetic fields, how will you take it? See, let's take this as the first circle and this as the second circle. All right, so as I've told you, if you're not familiar with the object or figure, whatever is given to you, then directly divide it into two parts. So these two circles are there, so we can divide it into first circle and the second circle. So first circle, okay, talking about first circle, magnetic field due to the first circle. Did anyone try this? B1. See, magnetic field at the center of the circle. At the center of the circle, what did I tell you? Magnetic field is mu naught I divided by 2r. Hania, can you tell me the radius of the first circle? Instead of r, what should I write? First circle is this. B. It will be B. So this becomes mu naught I divided by 2b. All right, now the direction. Samira, can you tell the direction for the first one?
It is K cap.
It will be K cap. Yes, right. See, moving along the sense of current. Current is moving anti-clockwise like this. This is anti-clockwise. So curl your fingers like this. This is the direction anti-clockwise. Curling, this is anti-clockwise direction. Thumb is leading away from the screen. Out of the screen means towards me. That is outwards. So outward means K cap. Then you have to write B2. See, the initial and the most difficult steps are this only, to write B1, B2, B3 and all these. Ultimately, at the end, you have to solve it mathematically. So that's not tough. And even the calculations are easier. For B, we have to consider not I. Current is 2I. So it will be 2 mu naught I by 2. Now regarding the first one. Now, Salman, can you try? This is the magnetic field. Radius of the circles are given. Can you try what will be the magnitude of this? B2. The formula I've written already. Salman is there in the class.
Ma'am, can you hear me? Yeah.
Yes, Salman. Salman,
Okay.
see, at the center of a circle, this is the magnetic field. I've already written the formula. Look at the second circle, this bigger circle. So what will be the magnetic field? Now you can try at least. Looking
UI
at
by 2.
mu naught I by 2.
2A.
2A, exactly. Mu naught I divided by 2A. Khalid, can you tell the direction? Oh, Salman, you can?
Yes, ma'am. Minus K cap.
Minus K cap, perfect. See, it is moving clockwise. If it is moving clockwise, curl your fingers clockwise. It will lead inwards. And even you can learn it by now. Clockwise always gives you inwards and anti-clockwise always gives you outwards. So yes, good, Salman. So this becomes what? This becomes minus K cap. Now you have values of B1 and B2. You just have to take the net magnetic field. So obviously both are in opposite directions. Net magnetic field will be what? B1 plus B2. B1 is 2 mu naught I by 2B K cap. This becomes minus mu naught I by 2A K cap because of negative sign because of this direction. So what we can do? We can take mu naught I by 2 common. No. If we take mu naught I by 2 common and K cap common, then what is left? 2 by B minus 1 by A. This much is left. This much Tesla will be your answer. In case in the questions, if the values are given, you can put in the values and calculate. Otherwise, method remains the same. All right, note down the solution. Let's discuss it now. See, you had to calculate magnetic field at the center of the circular coil. So two coils are given. Again, let's name this as the first coil and this as the second coil. Now see, when we talk about the second coil, this is not a thin circle given. It is a complete circle which is kept like this. First circle is kept in, firstly, let me tell you, this plane which is between this x-axis and y-axis, this is known as the xy plane. Then you have this, which is between the y-axis and the z-axis in the zy plane. And then you have this, which is in this plane, like this, between x-axis and z-axis. This plane means this part. If this is the y-axis and this is the z-axis, this is known as the xy plane. So in this question, actually, first coil is given to you in the xy plane, like this. And the second one, that is given to you in the zy plane. So the other coil is kept like this. It is actually a complete circle which is kept like this. This is the path, how they are called. This is the first circle, this is the second circle. So basically both are the circles only. You have to keep in mind, because the net answer will be given by the unit vectors. So you have to consider the unit vectors. Now for the circle, we have done the previous question also based on circle. For circle, it is mu naught I divided by 2r. Had it been a semicircle, for semicircle, it is mu naught I divided by 4r. So it is what? Mu naught I divided by 2r. Net magnetic field is equal to B1 plus B2. So net magnetic field will be equal to what? B1. Magnetic field due to the first one. See, magnetic field due to the first one will be what? Radius is A, current is I1. So that becomes what? Mu naught I1 divided by 2A plus the second one. Second one is what? Second one is current is I2, radius is B. So it becomes mu naught I2 divided by 2B. Now directions. All of you quickly write me the unit vectors. Right now, all of you. What should be the direction of first one and what should be the direction of second one? Remember their planes. What should be the direction? For B2C, this is the sense of current. Khalid, this is the sense of current. So like this, you have to keep your fingers. The current is flowing like this. And for B1 also, just check again. Current is flowing like this, clockwise. Others also respond, at least try. We can have a discussion, then I'll let you know the real answer. Others also try. Salman, you also try. Samaira, Sneha. B1. Okay, that was a typing error. Okay, yes, Khalid. B1 is right. Samaira, look again. It is moving clockwise, like this. This is the direction for first one. At least first one, all of you can write. Hania, Khalid has written. Again, Sneha, clockwise. See, like this, you have to keep your curl your fingers in this direction. Look where the thumb is going and use your right hand. I hope you're not using your left hand. Otherwise, this will be the direction what Samaira and Sneha are getting. Yes, Samaira. Now it's clear. See, it will be minus k cap. Yes, Sneha, it will be minus k cap. This is the were you using your left hand? What happened? This is the direction of flow of current. So inwards is all right. Just remember, always use your right hand. B2. Khalid, the axis is there in this plane only. This is YZ axis. So in YZ axis, if you curl your fingers, either it will be towards the left side or right side. At the same axis, you cannot get, no? So yes, first one is definitely curl your fingers along the sense of current. Thumb gives you direction. Hania, are you able to understand the direction, or should I repeat once? Hania? Okay, I'm repeating. See, Hania, for circular wires, when you ever have a circular wire, in which direction your current is moving, curl your fingers in that direction. For example, current is moving in this direction. This is what? Clockwise. So I have to curl my fingers clockwise. So curl your fingers clockwise. Try this at your home also. If you curl your fingers, this direction is what? Clockwise. Thumb is going inwards. That is minus K cap. If had it been anti-clockwise, means this direction, this is anti-clockwise, you have to see where your fingers are pointing. You have to check where your fingers are pointing, like this. If this is the case, this is what? This is clockwise. So thumb is leading inwards. That is minus K cap. If I curl it like this is what? Anti-clockwise. So thumb is where? Leading where? Outwards. That is positive K cap. So this way you have to see whichever figures are there, and then you have to check. Anya, is it clear now? Should I repeat again? Or any doubts in this?
No, ma'am, it's clear. Thank you.
All right. So for the first one, it will definitely be minus K cap. Curl your fingers clockwise. Thumb is pointing inwards. This is inwards. For me, right now when I'm doing this, my thumb is going inwards. It means inwards is which axis? Negative Z axis. So that becomes minus K cap. So B1 was the first one. No, this becomes minus K cap. Now B2 is left. Anyone can give the correct answer for B2. This is like this, situated like this, Z-axis and Y-axis. Means like this it is kept, and current is flowing like this. Like this current is flowing. For the second one. Current is flowing like this. So just move your fingers along the sense of current. See, obviously it cannot be K cap, because K cap's direction it is kept. See why it won't be K cap. Your fingers, you have to curl it where your current is flowing. So current is already flowing in the Z axis. So when you'll curl it in the Z axis like this or like this, either thumb will go towards the right or towards the left. So right or left is which unit vector? X-axis. Positive x-axis will give you plus I cap, negative x-axis will give you minus I cap. So it will either be I cap or minus I cap. And which it will be, you have to decide it by your own. How will you decide it? The figure, this was the circle. Now this circle, instead of being kept like this, it is kept like this. So the current which was flowing like this, now the current is flowing this way. So see, if I keep my finger, if I curl my fingers, this is the manner where current is flowing. If I look into the figure, see in this figure, current is coming and it is going like this. Can you see this? Current is coming and going like this. Top I2 is going. This is the flow of current. You have to enlarge your imagination, obviously, because drawing in 2 dimensions, 3 dimensions, all these figures, you have to think about it. So this is the direction of flow of current. For me, current is moving away from me, going into the screen, coming downwards towards me. Then again going up, moving towards the screen. This is the flow. So if I curl my fingers, thumb is leading towards the left hand side. So left hand side becomes what? Left hand side becomes negative x-axis, that is minus I cap. Now tell anyone who is having difficulty in this second part. Clear to all of you? How is it minus I cap? Right, try it in your notebooks right now. In your notebooks or on the screen also you can try. Sense of current. See, if I keep it like this, it is appearing as if current is coming towards me from the above. Current is not flowing like this. See in the figure, current is flowing like this. So this becomes, had it been given like this way, then see current is coming, then it is, then this is the flow of current. So this flow means this direction. But right now it is like this, so it will be minus I. Is it clear to all of you? Because this can be difficult. Because here you have to imagine all the planes, xy plane, it can be xz plane also. Had it been kept in xz plane, like this current is flowing, then it will give the answer in case of the other vector, that is your y cap, j cap, like this. So for x-axis, for z-axis, it will be minus I cap. All of you try it right now. If you're not able to understand, ask me. This will be your final answer, minus I cap. One last question I'm giving you, then we'll do a derivation. One derivation that is left in this circular part at the axis of a circle. But before that, I hope you've written the question, no? So just write down the solution and ask me which part, the magnitude part, the direction part, whichever you're not able to understand. Then I'll give you one last question and we'll do a derivation then directly. Okay, Salman. See, did anyone try? What is the answer you're getting? Let's divide it into two segments. This is the first wire, this is the second, this is the third, this is the fourth. See, magnetic field at point O due to second wire and due to this fourth wire. B1 net magnetic field will be what? Net magnetic field will be B1 plus B2 plus B3 plus B4. B2 it will be 0, B4 it will be 0 because the point is lying on the axis of it. So at the axis, if you take any point, if you consider any point, so sine theta is 0 and you don't get any magnetic field. Because of the first one, see, because of a semicircular arc, the magnetic field is given by mu naught I alpha. Alpha means the angle that is subtending, getting subtended at the center, divided by 4 pi r. So for the first one, mu naught, current is I, angle is what? Pi by 3. And then 4 pi. And then radius for the first one is 2r. This is 3. Plus 0 plus for the second one. So 0 for this third one. Third one is this again. What's the difference that will come? Everything will be the same except for r. So it will be mu naught I pi by 3. And here you have 4 pi capital R. So pi gets cancelled. This becomes what? mu naught I divided by 8. You have 4 into 2, and here it was what? Pi by 3. So it's 3, alright. So this becomes what? 24R plus 0, let's neglect it. Pi again cancels. Mu naught I divided by, this becomes 12R. Now the direction. For the first one, the current is moving clockwise. Clockwise inwards, minus I, minus K cap. For the second one, anti-clockwise, outwards, positive K cap. This will be minus K cap. This will be K cap. This will be your answer. All right, note it down. Then we'll do magnetic field at the axis of a circular coil if it is given. At the center, we did. If this is the circle, at the center, we know. If this is given like this, circle is given like this, then at this axis, this one, we'll calculate. First, note it down. Written. Should we move forward? Anya, Samaira, Sneha, written?
Yes, ma'am.
Yes.
Okay, all of you have written. Now this derivation, this is similar to electric field which we did for equatorial point. That time we made a triangle. Here it will be a shape of a cone that we see, but the derivation is similar to it. Now this derivation looks lengthier, but it's easy to solve. Magnetic field at the axis. So axis basically means what? This is your circle. Circle again has been kept like this. That's why I'm drawing it thinner. This is not in the shape of oval or something. At this point, for example, at this A point, if I have to calculate the magnetic field, then what? At the center, we know center is what? Mu naught I divided by 2R. And it's better if all of you remember all the formula of magnetic field. So do one thing, at least after today's class, try to write down all the formula of magnetic field on a sheet of paper for different cases, because you will get all the cases mixed up. So when you have all the cases mixed up, it will be difficult to recall whether it was 2 pi r in the denominator, 2r in the denominator, 4r, 4 pi r. This becomes confusing. So it's better if you remember all the formula for it. And magnetic field on the axis of circular coil, this has a bigger formula that you will see. So let's say r is the radius. This is r. All right, so this makes an angle of 90 degree, and at point A we are calculating. All right, so I have taken a very small portion of it. A very small portion, DL I have taken. If I know magnetic field because of DL, I can integrate it. Integration will result in the complete answer. So just consider us. So consider a small element, DL, and we can integrate to get dB if we integrate all the DLs that are present, small dl, dl, if we integrate it, because they are in the same direction, all are tangential, so you can ultimately add. One thing, direction of current. So let's take a random direction, because in your questions it can be any manner. Let's say this is the direction of current. All right, so we have considered small element. Now magnetic field A due to this element DL. Magnetic field at A magnetic field at A due to DL. Now we obviously have to apply Biot-Savart's law over here. So on applying Biot-Savart's law, yes, who can tell Biot-Savart's law? Hania, can you tell Biot-Savart's law? I think you were there on the first class. So if you are able to recall it, just try. I'll help you with it.
Oh, yes.
A constant was there. Do you remember the constant? Mu naught by 4 pi is the constant. All right. So do you remember on which things did magnetic field depend? On what quantities was magnetic field proportional to? See, mu naught by 4 pi is the constant. Current? Yes or no? It depends on current I. Anything else along with it? DL, that current element, sine theta. Okay, Anya, I'll help you. Sine theta, angle made between DL, means the small vector that we have taken, the current element, and the radius vector, and it is inversely proportional to R square. This is Biot-Savart's law. So obviously sine theta will be 90 degree. Reason you can directly see. Direction of DL will be like this. DL is over here. So DL is obviously tangential. And this is making an angle of 90 degree with it. So here the angle that will be between R and DL, this will be 90 degree. Sine 90, this becomes what? So dB will be equal to mu naught I dl divided by 4 pi small r square. This we have taken. Now we are considering DL where at the two extreme opposite ends. It means I should have this distance between the point that I am calculating and DL. That's when I will be able to utilize Biot-Savart's law. No, if I am taking another element here, then this value small r, let's say this is x. X is the distance from the center of the circle to the point. This is what? This is DL. All right, so this we have taken DL. Now R, X and this capital R, they can have a relation because of the Pythagoras theorem. So one thing we can do in this figure is that if I take the direction of it, magnetic field will be here because of this current element. This will be 1 dB. Then because of this current element, it will be another dB. So I have to do the resolution of vectors. I have to resolve this. Let's say this is angle theta, and let's consider this as angle theta. Fine. So if I resolve this along the axis, wherever you have to do resolution, along the x-axis or wherever the angle is made, you always get their what? Sine or cos? Along the axis where the angle is made, like here. Will it be sine or cos? Anyone? You don't know how to resolve vectors by now. We have done it so many times.
Cos.
Cos. Yes, Khalid. Why others are not answering? Yes, Hania, it will be cos. Obviously, it is cos. With whichever the axis is the angle made. This is known as cos. So this becomes dB cos theta. This becomes dB cos theta. And the perpendicular to it, this part will become dB sine theta. This part will become dB sine theta. Now see, this was just two DLs that I had considered. No, at all the diametrically opposite end, there will be DL, there will be DL. So all the cos theta, because of the current element DL, all the cos component will lead in which direction? Will lead in x-axis. And all the sine theta, if you people are able to see, half of the magnetic field will lie above the axis, half will lie below the axis. See, like this dB sine theta is getting cancelled with this dB sine theta. Similarly, all the sine thetas will get cancelled. All the sine thetas which are associated with the current element in the diametrically opposite end, that will get cancelled. And what will happen to the cos angle, cos component? All the cos components are leading in the x-axis in one direction. I had taken two DLs. There will be so many DLs. No, if I consider this corner, then opposite to this one will be the diametrically opposite end here. Similarly, so we can integrate dB if all dB or due to all the DL are in the same direction. So if I take this end, then obviously a counterpart will be here. So cos component will get added up. And what about the sine component? Sine component will get cancelled. And how do we know this? We know this because we have taken two elements and we had seen what happens. So cos theta was getting added up because it is in the same direction. Sine theta was in the opposite direction, so it will get cancelled. So what happened to the by will simply be what? dB sine theta I cap minus, not I cap, j cap, dB sine theta j cap This gets cancelled. Net magnetic field along the y-axis, this is 0. You have to add the magnetic field due to another diametrically opposite element. DL is also 0. I'll write down that also. Magnetic field due to other diametrically opposite. Don't think only 2 DLs are there. So many DLs are there like this. We are just considering the current elements that are associated diametrically at the opposite ends. So this is diametrically opposite element DL. This is also the same. That is same. So By will be 0, all the integrals of By. And what about x-axis, net magnetic field along x-axis? Net magnetic field along y-axis is 0. This is net magnetic field along y-axis. And what about the x-axis? X-axis we had seen all the components were leading in the same direction. So Bx will be equal to what? This will be dB cos theta. Is it clear till here? If this is clear till this portion, then you will be able to understand it further as well. Any doubts till now? Is it clear? Should I repeat any
Teacher,
part?
it's clear.
It's clear? Fine. Now, what is unknown? dB we know. This is dB. So, dB is mu naught I dl by 4 pi r square. Radius is capital R. So, dB will be what? dB will be mu naught I by, what was it, 4 pi capital R square, and dl is there. This is dB, this is value. Apart from this, apart from putting this as R square, we have to find out cos theta as well. So just look at this triangle in this. Cos theta we have to consider, no? So if this is the this is theta, all these will be theta, obviously. Theta, theta, it will also be theta. If you look at in this figure, then cos theta will be what? We have to find out cos theta, no? So it will become, this is theta, that has to be theta. Theta is taken angle between the current element and DL now. This will also be theta and that will also be theta. If we consider it in this, if we talk about this angle, so this becomes what? This becomes capital R divided by small r. In the triangle, cos theta is what? Cos theta is capital R divided by small r. So let's put in the values for the net magnetic field, because this will be only the net magnetic field. So B net will be equal to By, integral of By plus integral of Bx. So net magnetic field will be all the magnetic field that is associated with the x-axis, because for y-axis it is 0. So B net will be what? It will be mu naught I dl divided by 4 pi r square. This is because of what? This is because of the element that we have taken, magnetic field, because of Biot-Savart's law. And cos theta also we had calculated. This became r by small r. This we have considered. Now here, okay, one more thing before just this getting cancelled. See, capital R, we have to put it small r square only in this. We have to take the separation between DL and this point. No, so separation between DL and this point in this question, in this derivation, we have taken it as small r. So in Biot-Savart's law also, when we are deriving it in the derivation, we'll take it as small r only, because capital R becomes the radius of the circle, and we do not require the radius. We require the separation between DL and A point. So DL and A point, we can substitute it later in terms of capital R and X, but right now let's take it as small r only. We'll substitute at the end because small r is not given to us. So let's take it as small r only here. small r because we want the separation between dl and the point. So instead of writing capital R, because it will be confusing, no, earlier we used to write capital R because we considered the distance as capital R. Here capital R is given as the radius. So if we do not write it, no, so it will be confusing like this. This will get cancelled. But we know that this is what? This is separation, not the radius of the circle. So this will become small r square and we have to integrate it. So when you will integrate it, mu naught I capital R divided by 4 pi small r cube and then integral of dl. This much part has been written. Can anyone tell if I integrate all the dl's, what will I get? dl plus dl plus dl plus dl plus dl, all the dl's. Anyone from the class? What will I get? Radius is capital R. Yes, Khalid?
dB.
dB is the magnetic field. See, dl. All the small lengths, if I completely add it. Small dl's I'm adding. See, in the last derivation also we did it. When we integrated dl for calculation of magnetic field at the center of circle. Integration of dl, 2 pi r, yes. See, if you integrate all the dl, that means dl plus dl plus dl plus dl, all the small infinitesimal small current elements gets added up. So ultimately it will be what? The wire that is the circle. So it becomes 2 pi capital R. So integration of dl gives you 2 pi capital R. So magnetic field becomes mu naught I r into 2 pi r divided by 4 pi r cube. So pi will get cancelled, 2 can get cancelled. So what is left? Mu naught I r square divided by 2r cube. Now what did I tell you? R is not mentioned. Small r is not given to us. No, we have to write the answers in terms of x and capital R. X is there. X is the separation of the point at the center of the axis or the length of the axis. R is the capital R. Let me write what is X and what is R. So, but at least looking at this figure, you can say small r will be equal to under root r square plus x square. Let's just put in and substitute this value. Then I'll write down what is meant by X if it gets confusing. So magnetic field will be what? Mu naught I by r square 2, and instead of r cube, small r is what? Small r is equal to r square plus x square. Right now we had seen. So small r can be written as r square x square to the power half. We can write it. So this becomes what? This becomes under root r square plus x square whole cube. So the final answer for magnetic field, which you have to remember. Derivation is also not so lengthy. Derivation is lengthy, but it's not tough. Honestly, it's not tough. It just looks lengthy. You just have to put in, substitute the values of dB and cos theta. So this becomes mu naught I r square divided by 2 r square plus x square to the power 3 by 2. Now, capital R is what? Capital R in this formula, this is the radius of the circle. And X is the separation from center of circle to the point of calculation. So X will be given to you in the question, R will be given to you in the question. Small r might not be given. That's why we didn't write our final answer in terms of small r. So this is the final formula for magnetic field at the axis. Even if you put it x equals to 0, see, if you put it as x equals to 0, you will get it as mu naught I divided by 2r. So at x equals to 0 means what? At the center. So that also you can cross-check. So note down this derivation first. It's a lengthy derivation, but it's not tough. Just ask me wherever you get stuck. This time the point O is not at the center, it's lying on the axis. So radius is V, again the separation from the center of the circle to the point of calculation, that is X for both of it. Remember, this is given in YZ plane and this is given in XZ plane. So then consider the direction, see what will be the net magnetic field, try it, then we'll discuss. Take 2 to 3 minutes, then we'll discuss it. In this, one more thing, if n number of turns are given, no, so multiply it with n. That will become mu naught ni r square divided by 2 capital R square plus x square to the power 3 by 2, if n number of turns are mentioned. So in the question that we had right now, this is loop 1, this is loop 2nd. So we have to calculate the magnetic field. See, for the first one, just move your fingers along the sense of current. Just see wherever the current is leading. So this is the direction of current. So that gives me negative I cap, means minus I cap. All of you tell me the direction of current for the second loop. This one. At least try right now. Just write me in the chat box. I'll help you with it, whatever your answers. But at least you all should try it. For the second one. So only Samaira knows the answer. Others? Samaira, Hania have tried. Khalid, Salman, Sneha, your answers for the second loop. This is the direction of current in the second one. Current is flowing in this direction. Like this. This is the loop. This is XY plane, this is YZ plane, this is ZY plane. ZX plane. This is the direction of current. What should be the unit vector? for the direction of magnetic field. Yes, Neha, Khalid, Salman. No idea. See, this is now K cap. See, K cap, it is lying in that axis. So obviously perpendicular to it will be in Y direction. So Samaira's answer is correct only. This is the loop. This is the flow of current. Like this, current is flow. Loop is kept like this. So if you curl your fingers like this along the sense of current, this is the flow of current. Current is moving like this. This is the flow of current, no? So this is leading where? Upwards. Upwards is which unit vector? That is j cap. So that becomes positive j cap. So answer for the second one means the direction, that becomes positive j cap. So now the magnitude we have just calculated. Let's say n number of loops are there so that we can use it. So net magnetic field will be what? B1 plus B2. B1 will be n times mu naught current. Current that is flowing is capital I. This is the current that is flowing. Capital I. Radius is small b. So the formula, complete formula becomes n times mu naught I. Radius is what? A square. No, b square. Divided by 2 into b square plus x square to the power 3 by 2. And for the first one, it was minus I cap. This becomes minus I cap. Then we have plus n times mu naught I a square divided by 2 into a square plus x square to the power 3 by 2. And direction is y. J. All right, this is how you write your answers. Just noted this as well. So magnetic fields for different figures we have covered. Magnetic field for the center of a circle is mu naught by 2r, mu naught I by 2r. For semicircle that becomes 4r. For semicircular arc, it's mu naught I alpha divided by 4 pi r. For an infinitely charged wire, it is mu naught I divided by 2 pi a. And for semi-infinite, that is 4 pi a. Then we did the last case for magnetic field at the axis of a circular coil. So that is mu naught Ni capital R square radius whole square divided by 2 into whole square of radius plus whole square of separation from the center to the point to the power 3 by 2. Direction is given as move your fingers along the sense of current. When you move your fingers along the sense of current, direction of thumb gives you the direction of magnetic field. Like if it is in this manner in the XZ plane, if it is in the YZ plane, or if it is simply in your XY plane, simple XY plane that you have. Now, so note down all the magnetic fields separately, write down the headings, write down the formula so that you can remember. because at the end you will be having so many figures. Squares will be made up of finite wires, infinite wires. A semicircular arc can be joined by a single infinitely long wire and then connected to semicircular arc. Any question can come. You have lots of question, and do see the assignment also. In assignments also, I'll give you these kinds of question only. There are different figures are there. But the next topic that we'll start with it only, because obviously this is a very huge topic, and solenoid and toroid, all these figures are there here. So Ampere Circuital Law basically says what? If you have a current element flowing, according to Ampere Circuital Law, the line integral of a magnetic field around a closed loop, let's say current I is flowing across this. I current is flowing. Okay. This was the question with the solution. All right. So Ampere Circuital Law, no. So Ampere Circuital Law basically says that the line integral of magnetic field along a closed loop, like let us enclose this, along a closed loop that you have, that is given by what? The magnetic field around this is B dot dl. So line integral of magnetic field around a closed loop, this is given by mu naught times the current enclosed. The way you had Gauss law. In case of Gauss law, what did we write? In case of Gauss law, it was electric flux was epsilon 1 by epsilon naught times the charge enclosed. Here, the magnetic field inside for a closed loop, that is mu naught times the current enclosed. Mu naught is the same constant, that is 4 pi multiplied by 10 to the power minus 7 Tesla meter per ampere. Mu naught is that only, absolute permeability. Let me write down this. First, let me write down the law. The law says, according to Ampere Circuital Law, line integral of magnetic field along a closed loop this is mu naught times the total current enclosed by the loop. This is the exact statement, enclosed by the loop. So what is this B dot dl? B dot dl is basically this line integral of magnetic field. Let me rewrite that. This B dot dl, no, that I'm writing B dot dl. This is basically line integral of magnetic field. The line integral of magnetic field which I'm referring, that is B dot dl ultimately. Now, in this loop, no, if I consider again the small elements which I initially took, these dls which I took, DL, very, whenever this D term comes, means infinitesimal small. This is such a very small term that is there. So infinitesimal small term is there, DL is there. So this is the direction of loop, let's say. Direction of loop, not current. Current's direction is this. This is the direction of loop. Let me write down that. Direction of loop, not current. Means this is the direction of loop that we have taken. How have we taken the direction? Because these are tangentials. Ultimately, all these tangential added up will give the direction of magnetic field, like this. So this is basically, and this is also valid for a closed loop. So according to Ampere Circuital Law, basically, you have line integral of magnetic field, which is equal to mu naught by epsilon naught times the current enclosed. For example, if we just take this, a random figure I've taken, current I1 has this direction, I2 has this direction, I3 has this direction, and this is the direction of loop in the xy plane it has been given. And we are asked to calculate this line integral of magnetic field. So see, it will be mu naught times by the current enclosed. What is the current enclosed in this case? In this case, current enclosed, two currents are in the same direction, one is in opposite direction. For outwards, we put a dot. For inwards, we write a cross. So let's take inwards as negative. So total current becomes what? Focus on this. Total current will be I1 plus I3 minus I2. This is how you will take. So final answer will be this only. And this is what? This is the line integral of magnetic. And this is the line integral of magnetic. So just note it down, then we'll see what all things are left. Ampere's this law is known as Ampere Circuital Law. It was given by Ampere. So this law was named behind it, Ampere Circuital Law. So the way we used to write Gauss theorem as epsilon naught 1 by epsilon naught times charge enclosed. Similarly, write it for this also, mu naught times the charge current enclosed. Instead of charge, shift it to current. Written by now.
Yes, ma'am. Done.
And others? Done?
Yes, ma'am, done.
Yes, ma'am.
All right, fine. So I'm stopping here. Just revise